Hey, it's Paralyzed Math and History, and we are going to take a look at parallel lines in geometry. So, we've been learning about parallel lines in algebra, but for geometry, it's a little bit different. So, in algebra, we already know that parallel lines happen when there are two lines that are the same slope and never touch each other. So imagine if we have a graph right here, saying that this is the y and this is the x. We can say that these two lines are going to be parallel with each other, but they're continuous. So these two lines have the same slope in algebra, but they never ever touch each other. If I ever wanted to add a third line, but is perpendicular to these parallel lines at 90 degrees, then that perpendicular one that strikes through is called a transverse line. And not only that, this is the opposite of the slopes. Assume that these slopes are 3/4. Then the one that's the opposite, or the transverse line, which makes it perpendicular, is going to be -3/4 because it's the same slope, but going in the opposite direction. So that was the algebra idea with parallel lines. Lines that never, ever, ever touch each other.
It's as bad as it looks, Star Fox. We need your help.
Come on, let's give our boy some support. Hey, Fox, you made it. Bill, is that you? It's been a while. We've got a fleet to save if you're interested. Can you two save the cute banter for after we finish the job?
Yeah, let's get to work.
What about geometry? Well, let's get started and see what happens. So, plane. What is a plane? A flat surface. Well, that was a flat surface, but what about the mathematical term? Surface such that if 2 points on a surface is on a connected line, then all of the points are also on that surface. So it's stating is, imagine I have this right here. A line. Imagine if I have a point here and a point there. If I add another point on the line, it literally is on the line. Like here, and here, and here. So that is the mathematical reasoning for the term plane and surface.
So all we have to do is escape, and I've got immunity into the final 3.
That's right.
Whoa, how did you guys catch up so quickly?
Well, it was pretty easy. And now I'm going to win immunity. No, you're not, Flower. Oh no.
Huh? Wait, what does delete pull mean?
Good thing I can survive in lava. But not water, can you? Ha ha!
So if this is a 2D thing, and most surfaces are 2D things, like this floorboard right here, what happens if we try to do that on more of a 3D idea? Like, what if we say, instead of all of the points are on that surface, why can't we say that all of them are collinear? So in this case scenario, instead of seeing it 2D, assume that this plank goes through that plank. So we could say that orange and blue as points are on a surface that are collinear with each other. But the problem is, if we say orange and green, if we wanted to make a comparison with that, then we can say that they're non-collinear. right now, we are not going to give any symbols, just like congruent or perpendicular, because we haven't learned that yet in our class. So, instead of saying collinear, it's coplanar, because these are actually planes. 3D objects, not 2D objects. So we are going to complain that this is a 3D object, and we're trying to understand the points on the surfaces of that 3D object. Here's an example. So right here is an endgame for Vex Robotics I made. So with this mechanism, take a look at this thing right here. We have one surface and another surface. We can say that this right here and that right there, these two screws are on the same surface. They're coplanar. If I say this screw and that screw, we have to say that they're non-coplanar. These are not on the same plane. And that is basically what this is. The next thing we learned about was non-coplanar. So we demonstrated what not to do, and we also demonstrated what non-coplanar is. It happens when you have 2 points on 2 different surfaces. It's kind of self-explanatory, but now let's look at the most important part.
Oh no!
Huh? Wait, what does delete pole mean?
So just like congruent and perpendicular and bisector, parallel lines can have their own symbols too. If I draw 2 lines, and if I say that the first line is going to be point line A, line AB is going to be perpendicular. Line AB is going to be parallel with line CD. We could say that in an equation like this, line segment AD is going to be perpendicular with segment CD. Since these are arrows, we could say that they're lines because they go on forever. Some people have a habit of saying segment. If we wanted to do it in a shape, like a parallelogram, for example, then we would have to say G-O-K-L. These are going to be parallel, and these have to be parallel. However, you have to have 2 strikes, so you don't confuse them with the first pair that were parallel. So we can say G-O is parallel with K-L as segments. And on the other side, we can say G-K is going to be parallel with O-L. So the parallel symbol is self-explanatory. 2 lines that are vertically drawn together that look parallel. Now, since we understand what parallel lines are, and since we learned about the transverse lines of parallel lines, then why can't we go deeper into parallel lines? Why can't we understand this and start learning what this is all about? So, there are 2 parallel lines. We're going to say that line A is going to be parallel with line Z. And we are also going to say that line K is a transverse line. So these 2 lines are parallel, and this is the transverse lines. It makes 1, 2, 3, 4, 5, 6, 7, 8 angles! And a matter of fact, there are things that are named in this. Each and every angle has its very own twin, and it has its very own partner, and it has its very own name.